Welcome everybody to the Space Syntax Laboratory Research Seminar. I think I've said before that during these difficult times where we're having to find all sorts of new work practices, actually there are some sort of nice things that happen. And one of the benefits is certainly that for the seminar, we're able to ask speakers from around the world to join us, whereas previously that we would only have been really asking them if they had been in London. So really delighted to have Vinicius Neto speak to us today. Vinicius has been a long-term friend of the lab, student of Bill Hillier. Many of you will know his work, the paper with Bill, Society Through the Prism of Space, and more recently his monograph on the social fabric of cities. Really pleased to have you speak to us today, Vinny, and really looking forward to it. Thanks very much.
Thank you as well.
Thank you, Sam. Sorry, I'm sorry, Vinny. I'm just going to
remind. Go on, please. Sure.
Yeah, sorry. I'm so sorry. I'm just going to remind everyone that we're going to have like 30-35 minutes of presentation, and then we're going to have about the same time for Q&A. I'm just going to ask everyone to switch off their microphones so that we do not disturb the speaker. And after that, we're finished with the presentation. Anyone who has a question, we're going to take turn to ask the questions, and I will like to ask anyone who has a question to switch off their camera as well. Vinny, please.
Okay. So yeah, thanks a lot for inviting me. It's great to be with you and somehow be back, interacting with you guys at UCL. It feels like, home a little bit, because I've been there for 4 years and learned a lot, and it was a great experience and changed by everything that happened ever since. So it's great to be here and to bring this ongoing work about build form and entropy, and now how can we use entropy measures to understand build form and also segregation. This is pretty much ongoing work. So I'm just gonna throw you some ideas here. Essentially, I'll show you two papers. I'll compress two papers in a single presentation, which is always a bit risky because 30 minutes, 35 minutes are probably not going to be enough. So I'll cover a lot of ground, and I will refer you to the papers, and I'll ask you guys to go to the papers for details in terms of the state of the art and in terms of methodology and so on. All right. So I'll skip those details and the confrontation with the state of the art, especially. So this is pretty much a team effort, and I work with two physicists, Edgardo Brigatti and Fabiano Ribeiro, and PhD students, Camila, Caio, Yasmin, and Lucas, also collaborators in the research group here. So this particular work brings together Edgardo, Camila, Caio, and myself. So I'll open with this nice sentence here, this nice quote by Mike Patty. Cities themselves contain information processes. Indeed, they can be defined entirely by sets of social actors who are processing information in order to understand, explain, design, speculate, and decide in diverse situations. So this idea of cities containing information and information processes, as the idea that I've been exploring in the past 3 years, is about cities as systems of information. And back in Beijing, I think 2 years ago now, I introduced this kind of model there, this kind of theoretical conceptual model of the city as information in 3 layers. As you can see, a physical layer, which I called information 1, a semantic layer in terms of space, information 2, which is about, the information 1 layer, physical space, is about build form, is about street networks, visual cues, landmarks, and so on. Information 2, semantic space, is about the activities and social contents in buildings and the places where we perform. And information 3 is essentially about our actions in the city, how we create social systems, how we perform, communicate, we choose places to go, activities to perform, and how we create systems of interaction. All right, so you can see this information, this work in the paper there. I'll probably send you the link after the presentation. So this presentation here is essentially about the information 1, the physical space layer there. Okay, I'll focus only on that one, or mostly on that one, and see some connections with something in the information 3, the 3rd layer. So, okay, my colleagues and I are looking into the built environment and whether the built environment, this idea of the physical, tangible spaces, contains information. And I'm drawn to this idea of tangible spaces as opposed to the spaces we usually deal, for instance, in space syntax, which with a really interesting concept of space in terms of voids between walls and between buildings, if you will, like in form of streets and rooms. So what I'm addressing here is kind of the tangible parts of space, like the surfaces and buildings we can see and we can touch, and the fact that these arrangements of built form, if you will, they find, of course, a tremendous amount of possibilities, right? In terms of combinations of forms, like you have São Paulo there in Brazil with that really chaotic, kind of a chaotic or high or seemingly, random, if you will, arrangement of buildings in terms of positioning and height and so on. On the other hand, we have places or cities like Barcelona, which are much more ordered and regular in terms of buildings, built form arrangement, if you will. So we're looking into that. We're looking into information embodied in these elementary structures of space, which are the arrangements of buildings themselves. Like in those 2 images there, an ordered, regular kind of arrangement, and a more sort of a random arrangement on your right there. So we're looking into that, and we are essentially for methodological purposes and the way to approach this, looking for kind of a simple way to deal with urban form. We sort of work with a reduction from 3D structures to 2D structures of built form, just like in this the image you can see there. So we are handling 2D structures in this work. Some examples there: New York City, Rio de Janeiro in Brazil, Lagos, Nigeria, and Paris. So you can see very different arrangements of built form there. This amazing, ability of humans to create different arrangements there. So and of course, this is the reasons for these different arrangements are really puzzling and really, exciting and interesting to look into. So one reason to look into built form, you see there 2 images, you have the same street network and very different arrangements of built form. So you can see the same street network can support different built form systems, right? Which means that cities can be physically disordered, even if their street systems are perfectly ordered. So I'm puzzled by that, and I'm trying to understand how we can address this, let's say, this layer of tangible spaces there. So, and we are doing that using this idea of randomness, the idea of information, this relation between information and entropy to randomness, which is there in Shannon's Entropy, right? This classic work. I won't be able to talk much about it, but essentially Shannon relates entropy to unpredictability, with an uncertainty, the amount of possibilities of different messages you can transmit. That's his context as an engineer back in the 40s, dealing with cables and so on. So he related information to entropy and to the amount of possibilities of messages. So the idea of randomness is important for him, and also is important in the physics conception of entropy, which you can trace back to Boltzmann in the 19th century, which also relates entropy to randomness and unpredictability, if you will. So if what we have there essentially, to put this in really simple terms, you have on your left, you have a low entropy arrangement there with a really regular distribution of cells. On your right, you have a random distribution of cells, which you cannot infer the next position of a cell from the previous cells. Essentially, the arrangement doesn't inform you much about the position of every cell, whereas on the left, of course, you have a quite simple rule there, and you can infer easily the whole from the parts, if you will. All right. So we are essentially applying this idea to real urban areas, right? Just like New York City there, that section of Manhattan and that section of North Rio. And you can see there these, you can see very different arrangements of built form, same scale there. And you can also see there different combinations of cells which somehow are more frequent than others. So in New York City, you see those three windows I highlighted over there in red. You can see amplifying them. Those arrangements that are very frequent in Manhattan, like in facades and so on. On the other hand, you have in Rio lots of variations of cells, as you can see on the right. And our method essentially counts these different combinations of cells in squares, in windows, as we call, from like 1 pixel up to 25 pixels. And so we essentially count combinations within those windows, all right, up to 25 pixels, 25 pixels. So you see in New York City, little variation, more regular formations. You have a higher predictability in Rio, whereas in Rio you have high variation and poor predictability. So repetition, regularity, we are looking into those properties as potential information signatures, all right? So we can see, we can look into different levels of randomness and order in the arrangements of cells. So now we want to put this idea to use, right? And then connecting this with this nice quote by Bill, on a series of different cultural types and different scales embody different spatial identities. Human societies order their spatial milieu in order to construct a spatial culture that is a distinctive way of ordering space. So that's how I'm connecting this idea of this method of looking into entropy levels in built form arrangement to the possibility of identifying ways of ordering space and relate them to potentially to different spatial cultures or regions of the world. Okay, so that's the idea now to put this method to use. So for instance, you see there Barcelona again, and Lagos in Nigeria. You have probably different levels of randomness there and order. And for instance, the first hypothesis is there, different cities and urban areas are likely to have different levels of entropy and the opposite order. Okay, second hypothesis there is that the information signature of the entropy signature, if you will, of a planned area is different from that of an informal settlement. You have Copacabana and Rocinha in Rio, okay, an informal settlement. So, and also you have a third hypothesis there, which is if you have a sort of a top-down, strong systemic planning culture, say like in England or in Spain, or at least in Barcelona, you're likely to have different information signatures or entropy levels from a culture based on bottom-up processes, or what they call piecemeal planning, which is planning applied essentially to individual buildings instead of ensembles of buildings and areas. All right, so which is pretty much the case in Brazil, for instance, where I come from and I'm speaking from now. So we apply that method to 45 cities around the world. We do that with windows of 9 square kilometers. This is for reasons of computational reasons, all right, to make our measure work properly in terms of resolution and computational power, okay, and costs there. So we extract these maps from Google Maps, and this is the distribution of the cities around the world and the measures of the results in terms of entropy levels. There you can see from blue to red, from low entropy to high entropy, and you can see location of those 45 cities around the world. We are increasing this sample of cities, all right? But you can see some interesting patterns emerging there, quite exciting, and we are, looking into them at the moment. So if I plot these measures on sort of a sequential scheme there, you can see that Tokyo, São Paulo, Rio de Janeiro, you can see really high entropy there. Then you have another kind of cluster there, right? With Mexico City and Ecatepec in Mexico, Lagos, Nigeria, and Istanbul. Then you have another interesting kind of cluster there with mostly Southern European cities. Then you have a higher, kind of a low entropy, right? Lower entropy cluster there with American cities and Chicago and Beijing, which is the city with the lower entropy level we found, okay? And then we ran this proximity network analysis here. We found just to see these clusters in a different way, and you can see them there, different clusters there as entropy goes down to some American cities there. And so these findings essentially suggest that cities in different regions and cultures display different levels of order, right, in the way they arrange built form. This used to be, this idea of order used to be, in many works out there, used to be related to the idea of planned cities and unplanned cities. So, but we found that this goes a little bit beyond that. We found differences between strong planning rules, systemic planning rules based on ensembles, as I mentioned, and even the high entropy cities there. It's not that they don't. It's not the case that they don't have planning. They do have planning rules. Brazilian cities are. You find the higher entropy levels in Brazilian cities. At least the 3 we ran so far in this 45 cities set we have there. We do have planning over here, but it's a kind of planning which is really piecemeal, really centered on individual buildings rather than areas, right? So that's how we are trying to understand this. And so it's not so much about or only about planned versus unplanned cities. It's about the kind of rule applied, right? You can see this dendrogram there also showing this different, trying to identify some patterns there in terms of similarity, right? But this also can go beyond planning. This also may have to do with bottom-up historic trends, path dependency, and this kind of process there, governing levels of coordination, right, in the production of urban space. So these results make us think a lot, and we, of course, we are trying to figure this out. So this approach can tell us something about how much order different cultures invest in their built environment. So, but what else can we apply this approach of looking into built form through the lens of entropy as proxy to information or related to information, right? Can it tell us something about other forms of spatial information, say about social codes of interaction between people, especially between socially different people, right? So for instance, spatial information about where you are likely to live in the city or who you are likely to see on the streets, which is something very familiar with space syntax approaches, right? Would this spatial information be, with this probability, if you will, being somehow encoded in the various spaces around you? Well, we have some good ideas in terms that, yeah, of course, street networks have to do with how likely you're going to meet people, and especially socially different people. So let's see if this also applies to buildings, right? To build form arrangements. So we're looking now into residential segregation, right? Let's see if entropy in the built form has anything to do with residential segregation. We have some hypotheses there. It's the idea that urban forming encodes social distancing in its structure, and therefore informs us about the coexistence of different social groups, about ethnicity, racial groups, or income-based groups, which is the case I'm going to look into now, and which might impose limits or potentialize interactions between these groups, all right? So hypothesis there, different entropy levels may create the morphological conditions for the clustering of social groups. So for instance, areas with higher entropy levels may display greater clustering of socially homogeneous groups. So for instance, because it's probably entropy has to do with the way, with wayfinding, for instance, the way you can grasp information, extract information from the environment around you, and in order to make decisions about navigation, how you can get from A to B. And so that might have something to do with options for location, residential location for different social groups. Another hypothesis which runs in which is different from the previous one, higher entropy may be found in poorer areas with little or no planning. So this seems also reasonable, that you find, for instance, informal settlements with higher entropy levels. So we're going to look into those possibilities there. And then we apply the same method of this grid now to a single city with 9 square kilometer windows, right? With 1 million cells each window. And so you have São Paulo there in Brazil, big city over here, one of the bigger cities, the biggest cities in Latin America. So we first extrapolate data, right, like income from census tracts, and then we project them into this grid using this method of areal weighted interpolation. Okay, so how does this work? Going very quickly over this, we have the census tracts within the window, and then quite frequently you will find census tracts which are divided between two or more squares there, if you will, or windows, and then you have to make kind of arrangement there, a proportional arrangement in terms of the population according to proportion of area, which is cut by the division between windows. All right, if I'm not sure if I was clear about this, but that's a very simple way of extrapolating data into this grid. So for instance, you have there now applying one of the residential segregation measures, okay, which is Moran's index of segregation. So you have on your left census tracts in one of those windows in São Paulo. You have variation from low to high income in red, in reais over there, which is our currency. On the right, you have a measure of segregation, which as you can see, the orange and red census tracts on your left appear as red on your right, according to Moran, and your lower income sectors on your left appear on your right also as blue. Okay, they are highlighted. They are picked by the measure, and they are highlighted. So we apply this to every window or every of those squares in São Paulo. We ran a kind of a test here using Schelling model. I ran this simulation here with different levels of preference for neighbors. Let's say on this strip on the top there you have shelling, and then the first simulation there is a random distribution of blues and red cells, blue and red cells. B is when cells have, each cell has a kind of a preference of having 25% of neighbors equal to U, let's say. C preference rises to 33%, 50, 66, and 75% as you go around the simulation, and essentially the way that the whole system can satisfy a preference of 25% of neighbors equal to you means that you can only satisfy this individual preference by a collective kind of pattern there. And as you increase your preference for neighbors, like in this proportion of neighbors equal to you, the output, the only way of satisfying that preference is increasing segregation patterns. And then there you have Moran's index applied. And then you can see how this index increases according to those patterns there, right? And then you can see simulation E and F, they don't change much in terms of Moran. Okay, so we apply this measure for every single cell or every single window in São Paulo. There you have, we also looked into income, right? Income distributions on your left, Moran in the center, and Gini, we applied Gini measure of inequality for income on the right. So, and then we essentially compare this with entropy levels, all right? As you can see in this image here, you have income on your left and entropy levels on your right. And then you can see there's kind of some similarity there, kind of visual similarity, but also a lot of differences, right? So then we ran the correlations there between entropy, income, Moran, and Gini, and we found the most interesting result there, in my view, so far for São Paulo, entropy in built form and income correlation, Spearman correlation 0.30. So which somehow points in the direction of our impressions of our hypothesis that entropy in the built form somehow is related to the distribution of income in the city, which means that if you have an area with a higher entropy, you're also likely to find there, let me go the other way around, where areas where you find a concentration of people from a particular income level, you're likely to find a higher entropy there, or lower entropy, if you will. All right, so this somehow corroborates, I mean, this is only one city, right? But the idea that differences in entropy levels may create the morphological conditions for clustering of social groups. Right now what we're trying to do is we're trying to refine these measures and looking into other resolutions in terms of cells there and in terms of sizes for these squares. So also just to give you now another research subject here, we are also looking into the relations between built form, entropy in the built form, and what I call dynamic segregation. I've been dealing with this for some 20 years now, trying to see segregation in networks of movement of people in space according to income. You see there Niterói city in the Rio de Janeiro state, and you can see different income levels there represented by the colors, and how in this case 150 people interviewed a few years ago, and you can see segregation there. We are also attempting to correlate entropy levels with those distributions. You have here we developed this approach a couple of years ago, also using Twitter data to identify the networks of movement, essentially connecting the time and geostamp from every tweet in Rio during a particular period of time, a couple of days, and we connected those dots of those geo stamps and locations of tweets, and then we correlated them with income, and then we came up with those patterns, as you can see there, from lower income groups up to higher income groups, and then we overlap those layers, and you have this kind of pattern there, what I call dynamic segregation. This is still ongoing work. I don't have results for this correlation so far, but that's the idea, relating those three layers, right? Entropy, residential segregation, and dynamic segregation. So I think that's it.